All right, so welcome back, and in this lecture we are going to talk about polyhedra, and we are going to talk about the definition, the formal definition of what are the vertices for a polyhedron. Okay, so that's going to be coming up in this video. All right. Okay, so let us informally look at what vertices are. We already talked about this in the very first week, and we said, okay, let's see how simplex works. So simplex, we said, goes from vertex of a polyhedron to vertex of a polyhedron, and we said informally that vertices are these corner points. We call them vertices. We call them vertices. Singular is vertex, plural are vertices. All right. Now, let's formally study what are vertices so that our intuition can work for us not just in 2 and 3 dimensions, but for n-dimensional polyhedra. So even if someone gave you a 100-dimensional polyhedron of the sort that you cannot visualize, we will not go wrong. Okay, and I want us to get to that situation. All right. Okay, so let us first recall this notion of an active constraint with respect to a solution. So let me start with one solution. Here, let me start not the solution to this problem. So I'm going to forget about the objective. Okay, forget the objective. And just look at a solution in general or any feasible point in general. Okay, so if I take the feasible point 3, 11, which is right here. Okay, let me do a quick change of color so that whatever I show you can be visible. So 3, 11 is right here. Okay, and let me look at what are the constraints that are active for this solution. So what are active for 3, 11? And to facilitate that, let me give names for these constraints. Let me call this C1, C2, C3, C4, and then the x1 greater than or equal to 0 constraint is called C5, and x2 greater than or equal to 0 gets the name C6. Okay, now let's look at 3, 11. So what are the active constraints? So the active constraints are defined by constraints that are satisfied by 3, 11 with an equality. So what constraints does it satisfy with an equality? So it satisfies 2 constraints with an equality. Minus 3x1 plus x2 equals, right? So minus 3x1 plus x2 equals 2, and x2 equals 11, which are satisfying these 2 constraints with an equality. Every other constraint is satisfied with a strict inequality. So these are all satisfied by this point with a strict inequality, and that's fine. Satisfying it with a strict inequality also means satisfying it with a less than equal to, and satisfying it with an equality also means satisfying with a less than equal to. But rather than saying less than or equal to, I'm going to say, is it less than or is it equal to? I'm going to analyze the solution based on which case does it fall under, less than or equal to. If it's equal to, then the constraint is said to become active. If it's less than, it is said to become inactive. Okay, so 3, 11 activates 2 constraints. Okay, this constraint and this constraint, and if you solve these as simultaneous equations, you get the unique solution to actually being 3, 11. So geometrically, what this means is the intersection of those 2 lines has fixed 3, 11 as our vertex. Okay, so I hope that's clear. Let's take another point. Okay, so let's take another point. I'm going to erase some of this, or let me just erase everything and just restart. All right, so let's take another point, and here I'm going to take a point here. So I'm going to take this point 6, 7. Okay, so 6, 7. All right, which is going to be in the middle of these 2 vertices. So normally 6, 7 is not on a vertex, but it certainly lies on an edge. So 6, 7 lies on an edge. All right, now the question is, what can we say about 6, 7? What constraints does it activate? So looking at it, we will see that there's only one constraint that's activated by 6, 7. So 6, 7 activates one constraint, and that's going to be x1 equals 6, whereas 3, 11 activated 2 constraints. Okay, is that fine? So we can see now a pattern emerging. Let's take this interior point. Let's take this point 3, 5, which is right in the middle. So 3, 5, okay, which is right in the middle of the polyhedron. Now tell me, how many constraints does 3, 5 activate? How many constraints does it make active? Okay, and if you observed it, then you can say that 3, 5 activates 0 constraints. All right, so a vertex here in this 2-dimensional object, you can see that a vertex in 2D activates 2 constraints. Okay, and furthermore, it activates them in such a way that the vertex itself is defined as the intersection of those 2 constraints, where less than equal to is converted to an equal to. Okay, let me repeat. The vertex itself is realized as the unique intersection of those two constraints where less than equal to is made into an equal to. I hope that's clear. Now let's move on to the three-dimensional case and see what our intuition tells us. Okay, so in the three-dimensional case, let's look at a simple three-dimensional polyhedra, and for this I have the 3D cube. Okay, and I'll draw the axis just to be certain. This is the x3 axis, x2 axis, and the x1 axis. Okay, one of the corners is 0, 0, 0, the other corner is 1, 1, 1. So the vertices are 1, 1, 1. Okay, and this is going to be 1, 1, 0. Okay, and this is going to be 1, 0, 1, 0. This is going to be 1, 0, 0. This is going to be 1, 0, 1. So you can see there are 8 vertices. This is going to be 0, 0, 1. Okay, so there are going to be 8 vertices in this polyhedron. All right, now let's take one of these vertices, these so-called vertices, which I haven't defined yet, but we know from intuition what our vertices are. Let's take a vertex here. Let's take this vertex, which should be 1, 0, 1. x1, x3, and x2. Okay, now let's see what are the constraints in this polyhedron that it activates. So it activates x1 less than equal to 1, okay, x2 greater than equal to 0, and x3 less than equal to 1. So it activates 3 constraints. Let's take another example. Let's take this example here of a point whose coordinates are 1, half, and 1. Now how many constraints does 1, half, 1 activate? So 1, half, 1 activates 2 constraints, and you can see this geometrically. It's at the intersection of 2 faces, f1, and the top face, f2. It's at the intersection of these 2 faces, and you can see that the constraint doesn't activate, the point doesn't activate any other constraint. So it only activates 2, which is x1 less than equal to 1 and x3 less than equal to 1. So it activates 2. All right. Now let's look at another point, which is half, comma, half, comma, half. How many constraints does this activate? And you can say it activates 0 constraints. It's right at the center of the cube, and it doesn't activate any constraint. Okay. So in 3 dimensions, a vertex activates 3 constraints, and not just that, the vertex is uniquely defined as the unique intersection of the 3 faces that are defined by the constraints. So if you look at this vertex, there are 3 faces that meet here and uniquely define 1, 0, 1 as a vertex. So it activates 3 constraints which intersect at a point, and the point makes it a vertex. All right. So a working definition of an n-dimensional vertex, so if you take an n-dimensional polyhedra over x1 through xn, n variables, then we expect n constraints to be activated by a vertex. Is that enough? All right. So let us look at first some basic geometric facts to remind ourselves of these facts, and then move on from here. So the intersection of 2 lines in 2 dimensions yields a point. Is that always true? And the answer is no, it's not always true. The lines must be non-parallel. So if you have 2 non-parallel lines, their intersection yields a point. But if you have parallel lines, then no, their intersection does not necessarily yield a point. At least in Euclidean geometry, it doesn't. All right, so what about other, in 3 dimensions? So intersection of 3 planes in 3D yields a point. Is that true? Not necessarily. So you can have a case where the 2 of the planes are parallel to each other, or you can have other cases in 3 dimensions which don't happen in 2 dimensions. So you can have 2 of the planes intersecting on a line segment. Okay, I'm a very poor person to draw 3 dimensions. So you can have 2 of them defining a line segment L, okay, or a line L, and then the 3rd plane being parallel to this line. So the line, if the line is parallel to the 3rd plane, then you do not get an intersection of the 3 planes. Again, intersection of 4 hyperplanes in 4D yields a point. Once again, you need this non-parallel constraint. Okay, and when you get to n dimensions, it becomes pretty hard to imagine what are the conditions under which n hyperplanes intersect to give a point. So we go back to algebra, our very familiar territory, and we say n hyperplanes look like this. This is the equation of a hyperplane in coordinate geometry. a11 x1 plus a12 x2 da 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 a1n xn equals p1. That defines a hyperplane. So let's say we have n hyperplanes. Okay, when do they uniquely define a point? Well, that's just the solution of the system ax equals b, where A is the matrix a11, through A and N. It's the matrix that collects all the A's, and B is the vector of B1 through Bn. All right. So if the rank of A is N, or A is non-singular, okay, if A is non-singular, then yes, the N hyperplanes will uniquely define a point given by A inverse B. So much more elegant to write it. It's very difficult to actually give a closed form. It's going to become very complicated. All right. Okay. So I hope this is clear. So therefore, let us define a vertex. Okay. So we say a feasible solution X to these constraints is a vertex. So let's take a set of constraints. So let's say AX less than equal to B. Okay. Let's not worry about X greater than equal to 0. So we'll just say AX less than equal to B. And of course, the objective is no longer necessary because we are just studying the feasible region. Okay. So we say a feasible solution, which means the solution needs to be feasible. It needs to satisfy AX less than equal to B. Okay. And it's a vertex, okay, if and only if you have at least n inequalities being active. So if you look at all the inequalities that are made active by X, which means satisfied as an equality rather than a strict inequality by X, then we need at least n, okay, and the rank of the active constraints of X is n. Okay, what does that mean? If you collect the active constraints A11 through A1n, X1, Xn is equal to B1. So if you collect all the active constraints, there are at least n of them. Then the rank of the matrix formed by these active constraints is n. What does that mean? That means that if you look at them as hyperplanes, then they intersect and uniquely define a single point, which is X. All right, which means you don't have the cases where two things are parallel to each other. All right, and this is of great importance. So let me repeat what the definition of a vertex is. Okay, a vertex is a feasible solution X to the constraints AX less than equal to B. Okay, and it says that it activates at least n constraints, at least n inequalities become active for X, and the rank of these inequalities that are activated by X equals n. Very important. You need to understand that all parts of the definition, this part, at least n inequalities are active, the rank of the active constraints is n. You don't have to repeat it, it's the same thing actually. And the third part, feasible. These three parts are really, really important. If you drop any one of these, then you are done for. You no longer get a vertex. Let us illustrate that. All right. So does every point that activates n constraints form a vertex? In other words, what happens if I drop feasibility? What do I get? Let's take an example. So here is an example of a polyhedron that we call a polygon, we call trapezium. Okay, and it has 1, 2, 3, and 4 constraints. All right. So what does this mean? So this means that you can, let's take a point like so here. Okay, let's call this point P. So P activates C2 and C3. So it activates two of the inequalities, and this is two-dimensional. Therefore, is P a vertex? Okay, and the answer definitely is not, because P lies outside the polygon. So therefore, feasibility is very important. So what feasibility ensures us that is that points outside, which can be seen as saturation of two constraints, are not counted as vertices. This is of great importance. So P is no longer a vertex, even though it makes two constraints active. It makes C2 and C3 active. It's not regarded as a vertex because feasibility is first and foremost the requirement for being a vertex. It needs to be a point that satisfies the constraint in the polyhedron. Okay, second issue. Can a vertex activate more than n constraints? Is it even possible? So we define n constraints as being activated for a vertex. Can a vertex activate more than n constraints? Yes, it's definitely possible, and here is an example. Okay, let's take this example of a pyramid. Okay, the example here. All right, let's take one vertex here, V1, the vertex at the base. Now you can see that this vertex activates three constraints. Okay, it activates three constraints and can be seen as the intersection of three faces. Face number 1, face number 2, and the bottom face, face number 3. 1, 2, and 3. So it activates three faces. All right. On the other hand, let us look at the vertex at the apex of the pyramid. okay, the vertex here. Okay, let's call this the apex. Now, how many constraints does the apex activate? If you think about it, or if you look at this figure carefully, you can see that it's activating 4 constraints. Here is one face that represents the first constraint, another face that represents the second constraint, third constraint, and the fourth constraint. So all the 4 triangular faces, face number 1, face number 2, number 3, and the back face number 4, are all activated by this vertex at the apex. On the other hand, even though there are 4 hyperplanes, and your matrix has 4 rows, you will find that the rank is still 3. Which means if you fix any 3 of these faces, then the 4th one automatically comes through. Which means that the vertex is uniquely defined by any 3. You can choose any 3 of these 4, and the vertex is uniquely defined. The 4th one is just there. It's not redundant. Don't mistake it for being redundant. It's just that for that vertex, you just need 3 of them, even though 4 of them are meeting at a point and defining this vertex. And such a vertex is called degenerate. And we'll see how this relates to degenerate dictionaries. It's a very fascinating relation. All right, let's look at one more example. And here we have the apex where you have 6 faces meeting at the apex. Okay, 1, 2, 3, 4, 5, and 6. Oh, sorry, 5 faces. So 5 faces meet at this apex to form the apex. And therefore, the apex satisfies or activates 5 constraints in the polyhedron. Okay, and it's again an example of a degenerate vertex. So can a vertex activate more than n constraints? Absolutely. And finally, what if there are more variables than constraints? This is a very interesting point. Okay, so far we have assumed that if you have a polyhedron with m inequalities, then m is greater than n, so you can always find n, okay, a subset of n and activate. On the other hand, what if m is greater than n? Can we even have a vertex? And the answer is not quite. We will still have to define a point as a vertex, and let's take an example. So let's take a 2-dimensional example of a polyhedron that's defined by the single inequality x plus y greater than or equal to 0. That's just a single inequality. Okay, so it's everything above. It's still a polyhedron, except that here m equals 1, n equals 2. All right, so it has more variables than there are constraints. How do you deal with it? There are two answers to this. In linear programming, we had the standard form for a reason, and now we get an inkling of what the reason could be. All right, so in linear programming, when we brought together the standard form, one of the reasons was it automatically adds the constraints x1 greater than or equal to 0 to xn greater than or equal to 0 to the problem. And even if the problem wasn't in the standard form, we converted it to the standard form. And what that immediately gives us is it helps us make m plus n the number of constraints, because you automatically add these n constraints, and therefore the number of constraints is always greater than or equal to the number of variables. And it makes it easy to define vertices in such a case. On the other hand, take an example like this. You find that there is no natural vertex. A vertex should be defined as the intersection of 2 activated constraints, and you just see that there's just one constraint to be activated. Okay, so in such cases, we can automatically define a vertex either by converting it to a standard form and looking at a vertex of the standard form as a vertex of this problem, or we arbitrarily select a point that saturates or that activates x plus y greater than or equal to 0 and therefore makes it an equality. So we arbitrarily select a point on this line and just call it a vertex. Okay, so this is one case where the definition of vertex is fudged to add a vertex to the problem. Okay, and what we will do is we won't discuss this case much. It's not of great importance to us. So we will leave this case alone for the time being. But let's just note that you can just choose any of these points to be a vertex. And when we talk about rays and lines of polyhedra, we will revisit this example. Okay, so n-dimensional hypercube, as we know, has 2 to the n vertices. All right, so take the hypercube formed by the constraints 0 less than or equal to x1 less than or equal to 1, 0 less than or equal to xn less than or equal to 1. So every vertex is either a 0 or a 1, and it has n such coordinates. So you have 2 times 2 times 2, which is 2 to the n choices of vertices. Therefore, a 100-dimensional hypercube has 2 to the 100 vertices. That's a humongous astronomical number of vertices. So we see that polyhedra can have a large number of vertices, okay? And there is a combinatorial explosion, and the upper bound, if you have m constraints and n variables, assume m greater than n, the upper bound on the number of vertices is m choose n. Okay, why is that? So if you have m constraints, you can choose to saturate or activate any n of these constraints and hope that it defines a vertex. Although we saw that not every combination of n defines a vertex, okay, and some combinations of n will define the same vertex again and again. So we saw all of these, okay. Therefore, in general, the actual number of vertices tend to be much less than m choose n, but it's still an upper bound on the number of vertices. And if you have been thinking about dictionaries, then it's very clear there is a correspondence between dictionaries and vertices. And in fact, that's going to be something that we will study. All right, I said it. So in the next video, we are going to study the correspondences that exist between dictionaries and vertices. We will see that dictionaries are actually representation of vertices, and there is a very natural correspondence between dictionaries and vertices that we will study just now. Okay, I will see you in the next video, and thank you.